Settle down. Plenty of seat at the front. I don't think you gain particularly much sitting at the back because I'll go there anyways. Please come to the front. Alright, so we have been discussing about viscosity and there have been thinking many more problems about the things we have discussed so far. So, before we get further, this is something that we have done already. Please settle down. Stop that murmur. If you wish to speak, if you want to talk amongst yourselves, you can go outside. If it's class, I expect you to, have the courtesy at least to please quieten down. Okay. So one thing, one of you wrote an email to me is whether this is correct or not. This part. Okay. Now, one thing is when maybe I kind of in a rush said something else. So when I talk about centipoise, anything centi is 10 to the power minus 2 of that, right? So whenever I talk of centipoise, okay, so one centipoise, 1 cp, it's usually put like that, is 10 to the power minus 2 into 0.1 Pascal second, 10 to the power minus 3 Pascal second. Okay. So in case there's a confusion there, get that sorted out. Whoever wrote that email. And I believe for the second problem, we did correct it here. And to recheck the calculation. Okay, take this opportunity to make sure you're familiar at least with your calculator, so that your calculator does not become, something you stumble upon during the exams. Okay. These slides are shared with you, so, please make sure you can do the calculations properly. Alright. I'm going to show a little movie today. Okay. So, it's not from Hollywood or Bollywood. It's from, it's a relatively simple movie on something known as viscosity. Okay, which we have discussed yesterday. Okay, I'm going to speeden this up. So you have something which is very thick. This is, I'm told, this is corn syrup. Okay, whose viscosity has been put upstairs over there, and somebody is injecting corn syrup, at the bottom of this jar. You see, I'll just forward it a bit. 3 colors. And after you do this, what is done is 2 people take it and stir it. Can you see it? So you stir it. You can design this experiment with a less fancy device even in your, Fine, I stir it. So after stirring it, all the colors mix up, red, green, blue. Right? Very nice. Now, what they do is, they stop and they stir it. Well, he's still stirring. After a while, he's going to stir it back in the opposite direction. Okay. When you stir it back in the opposite direction, what do you expect? So you see the droplets form back again. Maybe not exactly in the same shape, but this is not an animation. This is a true experiment. Okay. So what gives? So we have those colors back. Feel free to design it. Go to some lab, maybe a physics lab, and do such an experiment. But what if I do it with my ordinary coffee? I take again same thing. I can treat the milk as a white paint, and that is my black coffee, and I'm applying a force when I'm stirring it, right? It's going to mix. It's going to give me my coffee. When I reverse stir, I'm not going to get my milk and coffee back, right? But the same thing, I'm applying force, whatever force I'm able to apply, and I can assume that my spoon and that stirrer, they're not more off by an order of magnitude, max, right? So what's going on? So let's try to understand this, and this is these look simple, but these are very important when you look at it from a biological point of view, right? You remember flagella and cilia, right? So your size matters, okay? Whether you are a living organism who is a micron size thing, whether you're a human, whether you're an elephant, whether you're a whale, okay? If I'm a Parmatian swimming in the sea versus if I'm a medium-sized whale, you know, the situation that I face is very different, okay? So, let's actually go back and try to understand what is viscosity. And clearly, you know, if you look back, if I step back, just note down the viscosity of water, 1.8 centipoise, okay? And viscosity of your corn syrup is about, suddenly this is not working because the battery has gone down, 5000 centipoise, okay? So 3 orders of magnitude different there. Now, what is viscosity? It is, you know, when I have a fluid, just imagine 2 plates and a fluid between that, and I'm applying a shearing force, and I'm pulling it with a constant speed V0. So the plate dragged with speed V0, you know, it's going to face an opposite reaction, you know, anything below it will try to move in the opposite direction. For some reason, my pointer is very weak, it's not working very well. I would appreciate it if you get some batteries, I do need this. So there's a resistive viscous force in the opposite direction. Here this is like 2 plates, but you can also have something which is cylindrical. Okay, so the drag, the resistive force felt in water, and you can imagine that will be much smaller than in corn syrup, glycerin, oil, so on and so forth, right? That is more of an intuitive feeling. But what is the real difference? The force that you are feeling in the opposite direction, I have put it at the bottom here, but in principle you can face the force anywhere along that thickness. Okay? Again, we are not going to go into very specific physical derivations. I'll just make these statements. Again, from an intuition, the force will be proportionate to the area of your plate, will be proportional to the speed with which you pull, and it will be inversely proportional to the point at which you are feeling it. Inversely proportional to D. I can make D variable as well, right? And because it's an opposite force, you know, not using vector algebra here, we have a negative sign. Okay? If these are proportionate this way, I'm just telling you that the proportionality constant is the viscosity of your medium, your Pascal second, your centipoise. Okay? So now you get it. If my eta is 5000 centipoise versus if my eta is 1 centipoise, it will make a difference on the resistive force you're facing, right? And eta, as we discussed yesterday, is a bulk property. Whether it's cytoplasm, whether it's a homogeneous fluid, whether it's a ternary mixture, whether it's air, whether it's carbon dioxide, it's a material property. It's a measurable material property. Okay. So what is going on here, you know, I have a picture of this, is very similar to your viscous drag thing. Except that it is, you know, this is hand-drawn, except that, you know, it is here in the circular regime. Alright. So what is really happening in this situation is, if I have a large viscosity, you know, from your Stokes Einstein, please, I think I would like you to step out. This is the 3rd time I'm noticing that. I don't know. Please come and sit here. It's not good for you. It's not good for my concentration. And, you know, please come and sit here. At the very least, this is discourteous. Maybe you guys don't care. I do. Okay. So when you have a situation of this kind, so what is going on is, if you have a large eta, your diffusion coefficient at your fixed temperature is small, for a fixed particle for a fixed temperature, right? Because eta D is proportional to your thermal energy, we know that. So when you have a small diffusion coefficient, okay, your your r square, your mean free path, the amount you can travel is actually very small, right? So before these guys, before your ink molecules, which are in a very viscous medium, their r square is so small that they have not been able to, within the time of studying, they have not been able to travel so much. So they are still local. So when I stir back, you can actually get them to come back. They won't exactly maintain the shape. Now one question you can ask. What if after the stirring, he immediately stirred back in the anti-clockwise direction? What if he had waited for, say, 6 hours? Would you get the same result? No. Till the time when, it has gone really a long distance, right? Because they have intermingled owing to their diffusion. Okay? Yes?
And that should work for coffee and milk too, right?
Good point. But then, coffee and milk, you see this 3 orders of magnitude difference. Your water and these things are traveling much faster. So, if you can design a very microscopic experiment where you can actually bring this about, that's going to be a technological challenge. But in principle, maybe you can have this effect as well. So nowadays, I understand what you're thinking. There is a lot of research in the nanoscopic regime. Okay, can we kind of pull these experiments off if we go to the smaller domains? That's where technology is going. So who knows? Maybe. Okay. So when you have this kind of a flow where it is organized, okay, and what is effectively going on is, your liquid, your thick liquid is moving in sheets, okay. Laminar, you understand the meaning of laminar, right? Like pages, right? So they are moving as sheets here. So this is laminar flow versus your coffee situation where the movement is much more chaotic. Okay, so this is turbulent or chaotic flow. Okay, now we are doing it because we understand, what are the ramifications when I look at biological situations. Okay. So here, of course, your eta is small. We looked at water, and your diffusion coefficient is large. Now, so let us assume that, as you just discussed, if I wait for a long time, or if the force was much higher, instead of a human moving it, maybe I attach a centrifuge to it. Centrifuge of 10,000 RPM or something. Then I attach the centrifuge in the opposite direction. Will I get my ink particles back, ink droplets back? No. Why? Because the force applied is much more now, right? So, for the same system, can I make a transition from laminar to chaotic, laminar to turbulent? So, can I think of a transition? By transition, I mean, from a laminar situation to a turbulent situation. Yes.
Instead of like a large force like a happening direction.
That's perhaps also possible, but you're talking about the direction of force which is changing. Technically, it might work. I'm not sure how we would establish that. Again, that's a hypothesis which will need to be proved. Okay, so perhaps that is true, but that's a good point. What if we keep the magnitude small, but we change the direction, which means you're changing the force itself all the time. So we can think about that. It's a good point. But let us, I'm going to predefine a quantity Q, and I'm going to call it is eta square by density of the medium. Okay, can you quickly tell me what the dimensions of Q would be? From yesterday's notes, you should know the dimensions of eta. I'm using eta square. Eta is, I believe, m L to the power minus 1 t to the power minus 1, right? So eta square is m square L to the power minus 2 t to the power minus 2, and density is m L to the power minus 3. So what are we getting? Is that right? Did we get it right? Anybody? Any skeptics? Okay, and this corresponds to the dimension of what? It's a force, right? So, what you can do is we can define a critical, again we are skipping over a lot of the physics. For this, there's definitive mechanics class, these should all be taught in specialized physics courses. But we are going to define a critical force, eta square, okay, square of the viscosity divided by the density of the medium. And this is where your system will, that is the amount of force which will divide your laminar regime to your turbulent regime. System dependent. Of course, this itself is situational. Eta square by rho m. Okay, this is system dependent. Okay, but here you see A, V0 and D. These are very much situation system dependent, right? So again I am telling you that if the force that I am applying, whether via a human being, whether via a centrifuge, whether via a machine, if your force is less than this value, you are in the laminar regime. If your force is greater than that, then you are in the turbulent regime. Okay. Now, let us quickly do some math. Okay. Simple math. Can you tell me what is, you can leave out olive oil. What is the critical force for water and concept in newtons? Quickly, can you calculate F critical? Eta square by rho m. I have given you the density, I have given you the viscosity, both in SI units. Rather, the question I am asking is for this one and this one. Okay, by what order of magnitude are they varying? Can somebody give me an answer? Yeah?
10 to the power 7.
Something like 10 to the power 7 orders of magnitude between your water and your consonant. Your cytoplasm might be more towards water, but you can definitely think that your F critical for your cytoplasm is more than that of plain water, right? Construct might be an extreme case. Hence, what is the ramification of this? We'll get to a few more specific problems there. So what we define, what is a very useful quantity, is something known as a Reynolds number. Anybody has heard of Reynolds number so far? Half the class maybe. So this is again a very useful quantity. It is nothing but a ratio. So it is a unitless quantity. Okay? And it gives you the inertial force. What is the inertial force? It is the force that you are applying. Mass times acceleration. Force, spark, whatever. It is the effective force in your favorite units that you are applying divided by the viscous force. Okay? Eta, that. Eta times A V0 by D. That kind of force. Right? So this number and the transition from turbulent occurs at roughly a Reynolds number of 1000. That is again a thumb rule. So in different contexts, we are going to try to evaluate how the Reynolds number is. What is the variation in life, and depending on that, how does an organism need to adapt. Okay. So if I am simply looking at, if I am a microscopic organism and I only have my flagella at my disposal, okay, whatever force I can apply, that is much less than, say, a human being who is swimming. Just compare the magnitude of force that you are applying when you are swimming versus what, your microorganism can apply when it is, transversing in water, right? So what is the situation? There's a situational difference. The medium might be the same, but the amount of force that you're generating, you're able to generate, that has something to do with your metabolism. So these are considerations that have to come in. Okay, so high Reynolds number flows more turbulent, low Reynolds number flow is more laminar, right? So one more quantity. So far, we have been looking at this value eta, okay, and we worked out the dimensions, we worked out the units and everything. This is known as dynamic viscosity, but again, skipping a lot of the detailed physics, there is another related quantity, and in a lot of textbooks as well as in literature, they will not report eta, they will report something known as nu, okay, which is more than eta and nu. Please understand that this quantity is the dynamic viscosity. Oops. This is the quantity that you have been introduced to so far, okay. So the kinematic viscosity nu is equal to, what is nu if you compare those two formula?
Rho by eta.
Your dynamic viscosity by the density of the medium. That subscript m stands for the medium. Okay. So this quantity is sometimes specified, but you can, I'm sure, this is now trivial. You can work out the dimensions of that as well. That's a trivial exercise. Okay. Now, so swimming is easily turbulent for us, as I was just saying. So imagine you are at our swimming pool, okay, and let's say your arm is anywhere between 2 and I don't know what is the weight of an arm. Anywhere between 2 and 10 kgs. For a child, it might be 2 kgs or less than that. And you are doing an acceleration. I'm ignoring directions. I'm ignoring torque and things like that. I'm just assuming that your acceleration is about 10th of g, 1.1 g, right? So the force that you are applying is 0.2 newtons of that order. It is the scales that matter. So 60 kg swimmer in water generates very large forces. Compare that with a unicellular organism. So let us actually try to calculate the inertial forces involved. The viscous forces, the F critical for water is the same. Okay, and we did calculate what was the F critical for water was. Going back, we compared the order of magnitude, but for water, how much was it in newtons? We did have F critical in water. For newtons, it was something like, no, F critical. Minus 3, right? Minus 9, yes, true. Oops, sorry. This keeps. So we are dealing with that amount of force. Okay, we are talking of nanonewtons. So if I'm kind of in that regime, for a human being, we are easily above nanonewtons. We are 9 orders of magnitude over what is required. So it will be extremely challenging to design an experiment where you can make water laminar. Have you thought about that? Can I design, a chip or something? There's something with such low viscosity as water is trained to be laminar. So I don't know if such a device exists. It will be very challenging because water at the microscopic level, we'll briefly go over it, is very unique. But in this case, I'm talking of a typical protozoa whose size is 50 microns, 5,000 nanometers. And its floating speed, okay, is 100 micrometers per second. Surrounding flow appears to be laminar. Can you establish that? How will you establish that for this entity, the surrounding flow is laminar? What will you calculate? Reynolds number. So you are going to calculate the inertial force, okay? But even without that, you can go back and use this formula as well. No, because we don't have D here. We can kind of scale up. We can assume we can assign a certain D, and we can, what we may do is, if I have, let's say, this microorganism, I can evaluate, say, the water around it. Okay, if this has a size of 50 microns, let's say I'm looking at 0.5 microns away, a sheath here. So what is the nature of flow of water at that spacing? That is something you can calculate for this. But how will I? So I've just made a statement here that the surrounding flow appears laminar. But how is it that you can actually establish that? So in any case, if we were to calculate the Reynolds number, okay, what would Reynolds number be in this case? I'm going to do again. I can do eta B A by rho n, right? I can use that formula. So eta will be 1.8 into 10 to the power 3, okay, 1.8 centipoise. I'm going to pick up my velocity from here. So I'm operating in divided by 10 to the power 3. So what is my Reynolds number for this microscopic organism? What is the mistake I made? 1%? Maybe the morning I did not have enough coffee maybe. What is it? Rho V by, what is it that has? Sorry, did I make rho V A by, oh sorry, okay, I just did the ulta, right? Yeah. So let's do that. So RE, so you're going to have eta here, you're going to have rho n here, you're going to have B here, you're going to have A here, right? So now what do we get? What is the Reynolds number that you're getting? And if I want to evaluate with respect to this benchmark, which is the regime that I'm in, is that okay? So what is the Reynolds number for a protozoan which is floating in water with its natural floating speed? What is the order of magnitude? At least give me the order of magnitude.
Approximately 2.5 into 10 to the minus 3.
Something like 10 to the power minus 3. Others? Anybody else? It is certainly much less than 1000, right? And I can give you a situation where you have some kind of a directed motion. Some of these organisms can actually speed up. 100 microns per second is the floating speed. There are certain smart microorganisms also which can actually, it can expend energy and move in a certain direction. Okay, but altering it by I have to cross 6 orders of magnitude in my Reynolds number in order to achieve turbulent flow, right? That is, again you have to go back to the situation it is in, right? So for this case, RE is of the order of 10 to the power minus 3. Anybody who got a different value? Okay, So please keep these things in context. Huh? So with that in mind, let us do, I think we are going to finish a little ahead today, but we'll do some problems in the tutorial class. Huh? So we'll probably let you go at least 10 minutes ahead today, unless you have questions. If we look at this situation, plankton are passive organisms in seawater. Largest plankton measures about 20 millimeters. Okay, so I'm going to say A equal to 20 millimeter. Okay, so 20 into 10 to the power minus 3 meter. Okay, what are the ranges of the Reynolds number at 20 degrees C and 20 degrees centigrade? Huh? So we don't really need the temperature here. The viscosity is a function of temperature. You need not, somebody can give you a plot just like we had yesterday, where you are, from an experiment or from some data, we are finding the viscosity at a particular temperature. But other than that, you can treat it as a parameter, something which is given to you. Okay. So the viscosity of pure water at 25 degrees is given. Viscosity of seawater at 20 degrees centigrade is given. Density of seawater at 20 degrees centigrade is given. Density of pure water at 25 degrees, 10 to the power 3 kg per meter cube. You know that, right? So that data is not given. So you have eta 1, eta 2, eta 3. Okay, and correspondingly you have density 1, density 2, density 3. Can you tell me, I want you to do it, what is Reynolds number 1? What is Reynolds number 2? What is Reynolds number 3?
Please, that is the density of seawater, not intensity.
That should be, what is it? Yeah, so that is the density of seawater. I'm sorry, I did not. Let me edit that again.
1.2 into 10 to the 3.
From 10.3.
One person tell me what is wrong here?
1.2 into 10 to the 3.
Yes. The density of seawater at
1.2 into 10 to the power. Correct. It's obviously, if that's a typo, 1200 kg per meter cube. I'll correct that. Alright, so viscosity is given. So let's omit all these things. So this is, you have viscosity of 2, okay, and this is density of 2, okay. We need 2 of these. It's not 3 choices. It's, I think we have 2 situations, right? We have seawater at 20 degrees and pure water at 25 degrees, right? So are they comparable or do they significantly differ? The question is, to what extent do they differ? So is that okay now? And there can be variable situations as well. You can have a heterogeneous mixture. You can have some of these gels that you guys prepare. In microbiology labs, they create a lot of these environments. If you're working with somebody doing research on microscopic organisms, they make these amorous gels and so on and so forth, where you can actually keep track of the viscosity as well. So what is the Reynolds number in the first situation? Should not be difficult to calculate. Density into speed into size divided by the viscosity, right? So the first situation is pure water and the second situation is seawater. The temperature is different, but that should not bother you. Which one? 1 or 2? 4.48. Okay, of the order of 4.5. Is that right?
Yes.
Right? Anybody got 4.5? Great. Second situation?
In the question we are asking for the range of the Reynolds number. So we have to make two calculations for the Reynolds number for each case of seawater and pure water respectively. Because two lengths are given.
Right.
Are they asking for the size to largest to smallest or pure water is
No. So I understand the question is a little confusing, especially because two temperatures are given. So if you read it, so the distance covered is given. That's not a question. What is given is pure water at 25 degrees. Yeah. So what is confusing is what are the ranges of their Reynolds number. If I switch this part off. This part is confusing. So let's lift out the temperature. Is this okay? No, if we have pure water, okay, right. So what your question is, it is traveling roughly, they cover their own length per second in water. So you can assume that whether it's seawater or whether it's pure water, it's covering its own length per second. The idea is to just get the Reynolds number and see, if they are really differing in the different situations. Yeah. Right. Oh,
can be from largest to smallest. That's the range they are asking.
Right. And the smallest measure about 2 and this is 20. Right. Yeah, sorry, I should have been a little bit, I apologize. So there are two situations. This is not, let's clear this out. Okay. We have some time today. So let us look at it this way. You can draw a scale of this kind. No, I could have called it largest. Okay. You can do pure water. You can make a chart of the Reynolds number of this kind. Right? Do you have the adequate information to cover this table? Or is something missing? I see some unhappy faces, so let me know what is missing. So I understand that there is a 5 degree centigrade difference, but in the context that you are given, is there some information missing? Yes. Can you repeat that again? So if they say in water, you can make that assumption that they are roughly medium water. So in this case it's going to be 20 micrometers per second, in the other case it's going to be 2 micrometers. So when you talk of microorganisms, okay, or unicellular organisms as in general, we actually talk of the movement, coverage of the same dimensions per unit time. If you go back to the very early classes, first or second or third classes, when we were doing dimensions and things like that, we were comparing a human runner to a microorganism moving. And the scale that we covered is, how many times your own size per unit length. Remember, I think we talked of a runner in the speediest runner as well as a bacterium and things like that, right? So we are always going to, so that's a useful benchmark. If you're talking of, say, a rabbit, which is what? Maybe a feet? Okay, 30 centimeters or so. So if a rabbit is moving, how many units of its own length can it cover per second versus if, a human being is running, how many units of his or her own length a normal person can cover. Same with the bacterium. So that will deal with your question, smallest and largest. That is a very typical measure. That is something you will encounter very frequently in literature, in scientific writing. Okay, we talk of how many units of your own length per unit time. So in this case, you can then fill in the blanks here. Tell me what are the values? Which one? Okay, tell me this one. How much? 4.49? Smallest and pure? I'm going to round it up to 4.5. Largest? So it changes by 4 orders of magnitude. Seawater? Same, right? Oh, this will be 10 to the power plus 2. Okay. And these two? So at the end of the day, this kind of fits your intuition. I don't expect the situation to dramatically change when there are more salts added to water. Slightly different. I mean, the density of pure water and seawater are not off by orders of magnitude, right? I'm sure you've experienced seawater. Of course, it's slightly more dense, say 1200, from 1 into 10 to the power 3 to 1.2 into 10 to the power 3. The thing to realize is what are the dominating factors here. So once again, size matters here. Okay? So we are changing by 8 orders of magnitude, but still we are falling short of Reynolds number of 1000. Okay? So at the end of the day, your largest plankton is perhaps unable to achieve turbulence. Did you hear that statement? So your largest plankton, which we are saying it is of the order of 20 millimeters, let's say, even that organism will not be able to achieve turbulence in water in general. Okay, but within, let's say, the plankton family, you can skip by 8 orders of magnitude. Okay, so that is the other key lesson here, that in such considerations, when you're considering different situations, you have to understand how your variables will influence these numbers. So let's say now we are kind of, we have an extremely, I don't know if it's possible to have any other fluid, any other liquid which is less viscous than water. I'm not aware of, if anybody is aware from their own readings, you can tell me. No, I'm talking of a liquid. Of course there is a fluid. Gases are fluids. That's again going to be orders of magnitude less viscous. But your plankton will not survive in air. The medium in which you are surviving, can you actually, have some medium which is even less viscous, a liquid which is even less viscous than water? Oil is more viscous. Oil is more viscous. So we have a question with olive oil. Okay, its density is less, but its viscosity is at least 1 order of magnitude more than water. You can feel it, right? So your oil is a different situation. Huh? So again, another lesson that is coming forward is, everything, all this biology is really happening in water. So if you were to replace water with something even more viscous, you'll end up with replacing the medium with something more viscous, that can actually fine-tune many things, such as metabolism. Today we'll do one problem. We'll go back to what we have learned previously and look at how, you can use, if you have a nutrient profile, we'll actually get back to Fick's law and see how the nutrient supply can be used up. So these are, questions within the context of biology. We'll briefly, look at some characteristics of water as well. Then we'll move on to more examples, okay? And that's it. I think I really don't have anything more for today's class unless there are questions.